Buenas tardes a la comunidad del ICAT. En esta ocasión, en este martes de coloquio, tenemos la presencia del doctor Michal Vopálenský, del Laboratorio de Tomografía de Rayos X, del Instituto de Mecánica, Teórica y Aplicada, en la Academia de Ciencias de la República Checa. El doctor Vopálenský nació en Jihlava, Checoslovaquia, en 1978. Estudió en la Facultad de Ingeniería Eléctrica de la Universidad Técnica Checa en Praga, donde obtuvo la maestría en medición e instrumentación en el año 2002, realizando un proyecto final parcialmente en la Universidad Técnica de Viena. En 2003 obtuvo una beca de la Secretaría de Relaciones Exteriores de México para realizar un proyecto de investigación en el Centro de Ciencias Aplicadas y Desarrollo Tecnológico, ahora ICAT, en la UNAM, en el laboratorio de microondas con el doctor Oleg Kolopotsev. Obtuvo el grado de doctor en Praga, en la especialidad de medición en 2006. En ese mismo año se mudó a Irlanda para colaborar en el Tyndall National Institute, en donde trabajó en un proyecto de diseño de componentes electrónicos. Al regresar a la República Checa, trabajó 4 años como especialista de inspección automatizada y procesamiento de imágenes en Bosch Diesel, y desde 2011 trabajó en el Departamento de Electrónica e Informática de la Universidad Politécnica en la ciudad de Jihlava. En 2015 se convirtió en profesor asociado en la Universidad Técnica Checa en Praga y desde ese mismo año es el supervisor del Laboratorio de Tomografía por Rayos X del Instituto de Mecánica Teórica y Aplicada de la Academia de Ciencias de la República Checa. Actualmente se dedica a la optimización de los procesos de adquisición de datos, desarrollando nuevos métodos de tomografía y procesamiento de imágenes con un instrumento experimental Toraton. Es el autor o coautor de más de 20 artículos en revistas indizadas y decenas de contribuciones en conferencias. Tiene más de 300 citas y un índice H de 10. Pues muchas gracias por su participación, doctor. Bienvenido y estamos atentos a su charla.
Gracias. Muy buenas tardes a todos. Yo tengo que decir que no estoy nuevo aquí en México y aquí en el instituto, como ya se había dicho. Y entonces voy a empezar a hablar o a dar las primeras hojas aquí en el español, pero luego voy a hablar inglés, ¿no? Mejor. Y entonces el tema de mi plática es los avances en la tomografía rápida para particle tracking. Bueno, entonces, ¿cómo empezó todo? Entonces ya, como se había dicho, en el año 2003 yo estaba aquí en este instituto con el doctor Kolopotsev para 10 meses en el laboratorio de microondas. Y luego cuando regresé al piso académico, digamos, a la Academia de Ciencias, estaba buscando las posibilidades de pues renovar la cooperación con México. Y luego aquí estaba invitado a la Mexican Meeting con Additive Manufacturing en el año 2018 en el Madrid. Y aquí en Madrid estuvimos también platicando con el doctor Leopoldo Ruiz y el doctor Alberto Caballero, que ellos estaban desarrollando un esófago humano, un modelo de esófago humano, y que le interesaba caracterizarlo por rayos X, pero para hacer esta cosa siempre se necesita una velocidad rápida y también una buena resolución. Y ya que nosotros en la ciudad de Telch, en la Academia de Ciencias, tenemos un equipo que lo llamamos Toraton, que está patentado, y tenemos también un juego de detectores que podemos utilizar, pues lo vimos como una buena oportunidad de tratar de medir o caracterizar este esófago dentro de este equipo. Y luego, entonces, en el otoño de 2018, doctor Leopoldo Ruiz y doctor Alberto Caballero me visitaron en la República Checa e hicimos los primeros experimentos con el esófago en el equipo Toraton. Y luego yo me traje en mi otra visita a México en el año 2020 me traje el modelo de el esófago a la República Checa para hacer los experimentos ya mejor hechos, ya con un poco optimizada la velocidad de scanning, y para tratar de hacer una reconstrucción de las partículas en el bolus en 3D. Entonces, eso sería la historia, y ahorita ya voy a seguir en el inglés. So, what is the context and the motivation of the all work done in this project? If we have a dynamic process, like a physiological process, we always need a high scanning speed if we want to characterize it with the X-rays, because the process is changing the form of what we are observing. So our scanning speed has to be much faster than are the changes of the reality that we are observing, of course. But in the recent times, the technological advance allowed to get to the market the detectors which have really very low exposure times, like in order of tens of milliseconds. Then the Toratom device that we have in Telch has the possibility of viewing the process from 2 directions. And then we have, of course, a lot more information than just seeing that from one axis. So the question arose that if it would be possible to exploit our Toratom device to get a 3D model of the particle movement in the model of esophagus made here at ICAT. This is the model of esophagus designed here in the laboratory of additive manufacturing. So you can see that there are 6 levels of pneumatically controlled chambers, and by appropriate control with computer-controlled valves, you can generate a peristaltic wave, which then translates the bolus through the duct of the esophagus model. As the bolus, we use the children food with aided barium sulfate, because barium sulfate is a good contrast agent when used with X-ray. One cycle of the transport of the bolus is 9 seconds in case of this esophagus, and just here I see that there is no scale. So this dimension, it means the height of the esophagus model is 130 millimeters. This is, on the other hand, the Toratom device which we have in Telch. So you can see that there are a lot of axes that we can move, which is one of the main advantages of our Toratom, because the geometrical variability allows us to get the magnification from some 1.2 up to 200. So if we then combine it with detectors which have the pixel size of 200 micrometers or even 100 micrometer, we can get the resolution below or to the order of 1 micron per pixel. There are 2 orthogonal axes which are equipped with both with its own X-ray source, and there are 2 detectors or detector supports, let's say, because as I said, we have a set of detectors that we can use. And all these axes are controlled from the computer, so we can quite easily change the geometry of the whole device. We have there 2 tubes which are not equal, which are not identical. One tube has 240 kilovolts as the maximum accelerating voltage and the power of 260 watts. And the second one, this one, has the maximum acceleration voltage 160 kVs, and it has the maximum power of only 125 watts, which was limiting for our experiment, as we will see in a little bit. Because, well, if you need a big power and if you want to use both tubes, it is very nice that you have here more than 200 watts, but you cannot use it if you want to have the same, let's say, illuminating conditions, and you are limited by the weaker tube having only these 25 watts, and even these 25 watts are not really stable. Okay, so this is a photo from that fall 2018, where we gathered in touch with Dr. Luis and with Dr. Ruiz and Dr. Caballero, and they brought the model of the esophagus to Telch, and we made the first proof of concept, if it is even possible, to think about using Toratom for scanning of this object. We used one Varex Dexela detector at the full resolution, which is 1536 per 1944 pixels, and the exposure time, and this is the shortest exposure time with this resolution, it was 40 milliseconds. But I didn't have good scripts because, as I said, this device is developed by us, so I'm also developing always the scripts for data acquisition and for movement and for all. And I didn't have that time good scripts for optimized data acquisition with such a short exposure time. So we had some data transfer limitation, which then led to the fact that we made each image with the exposure time of 40 milliseconds, but there was some time needed for the data transfer. And at the end of the day, we got 12 frames per second exposure rate, let's say. As well, you can see that there are these connections of the hoses, of the pneumatic hoses, which then obstacled a little bit the view. It is better viewed here, because here what we see is what we got actually from that experiment. So I will move it a little bit to other exposures. We can see that the movement of the particles is observable, and we can also see that there are these obstacles of view. So in the next generation of the esophagus model, it was developed in a different way. So this was our first experiment. Then the guys here at ICHAT were able to take those images that you saw just now, and using the digital image correlation and extensive analysis of the subsequent images, they were able to develop the images of the velocimetry fields in the bolus transformation. So actually that experiment was very successful, because we, after that, published the results in the Journal of Visualization in the year 2021. But there was still this question, because we knew that we were able to make some fast scanning in one direction, but would it be possible to use the two orthogonal axes that we have in Toratom device and make the 3D model of the movement of the particles in the bolus? Well, if we talk about this possibility, we could say, so we just extend the principle that we used for the velocimetry field extraction in 2D. So it means comparing the images and looking at where the particles moved in between two images, but we just will do it in 3D models. But first for that, and we will do it in the way or with the method that we call the digital volume correlation instead of digital image correlation. But okay, for 3D model, you need tomography. And in the classical tomography, which looks like this, let's say, you need a high number of views from different angles, and from this you then can reconstruct the 3D model. So if this is the object, this puzzle here, and you rotate it, you will get at the detector subsequent images of how does it look like from different angles. And then taking this data set and making some calculations, you can reconstruct the 3D object which you actually observed. But this is the most regular way how to do that. But you have to rotate the object. And if we are talking about the esophagus or about similar things, the rotation with the object can influence the process, of course. And as well, in the case of esophagus particularly, you have connection issues, because this is how it looked like when we did the first experiment. And you can see that there are always cables, hoses, and so on. And making a fast rotation with this is not really, well, imaginable, let's say, if we want to make more rotations. There is another possibility which is used in medicine. Here I have, I'm sorry, but I have here some Czech designations. This means the X-ray source, these are the detectors, this is the object under observation, and this is the X-ray radiation. So here is the object, and we just move the X-ray source and the detectors, like you know that from the tomographs which I use in medicine. But of course, again, this is quite complicated to build. And as well as in the case of movement with the object, we still have this limitation which says that the process cannot change too much, or let's say the structure of what we are observing cannot change too much during one rotation. So it has to be quasi-static during one rotation. And if I said that the process of the entire swallowing of the bolus in our esophagus model is 9 seconds, you can imagine that it is moving, like the bolus and the particles in the bolus are moving quite rapidly. So you would need really large rate of scanning. So the rotation speed is often not realistic in that case. Is there any possibility of having more exposures, more angles, and not moving anything? Okay, yes. There were some experiments done, and they are reported in the articles, that you use simply more imaging access. So you have 1, 2, 3, 4 sources, 1, 2, 3, 4 detectors, and at one moment you can get 4 angles of the observed scene, and as said, at the one moment. But you can imagine that building such a device is very expensive and very difficult. So I know that they were using some devices where they had 8 imaging access, but it is not something that you would build simply in your laboratory. If we talk about this possibility, then the extreme number of angles, the minimum number of angles that you can have are 2. So yeah, it is the case of Toratom, of our device, for example. But in that case, the reconstruction is quite difficult, and it is ambiguous as well, as we will see in a little bit. There is also a question if the 3D model of the scene of the particles is even needed. And talking just about velocimetry, well, not necessarily, because you can analyze each detector. So in the case of 2 detectors, 2 orthogonal detectors, let's say this is the real example that we have from our experiment in Toratom with the esophagus. So you can match the particles between the views. So this means this is one detector, this is second detector, and you can say, well, this particle here is very probably the particle here. Then you look what happens in between. You can see the movement of the bolus, and you know where the particle moved. Okay, so if you still can match those two, then of course you can from this estimate the vector of propagation in one direction and in orthogonal direction, and you have the possibility of extracting the velocity field. But of course, the correct matching of particles on the individual detectors is crucial. And if you look at that, at the noise that we have here because of short exposure time and all these things, you can imagine that making this can be very demanding to be programmed, let's say, and to be done automatically. So it is possible, but very difficult. And our experiment relies on the 3D reconstruction of the models, and then making or preparing the models for the velocimetry in 3D, comparing the subsequent 3D models. So this is what I did before Christmas 2019, I think, still, or maybe 20. This is the experiment which was intended to get the information of the bolus transport in 3D. You can see that we have here two Dexela detectors, that here the hoses are connected in a different way. So there are not these obstacles made by the connectors from plastic anymore. And I used for this experiment, as I said, two Dexela detectors. And I did two experiments because I knew that in full resolution with 40 milliseconds, we would be able to see the bolus, because we did already that experiment with 40 milliseconds. But going to the limits, I also made second experiment where the exposure time was only 15 milliseconds. So it means I was able to make 66 frames per second, but in half resolution, because we used the binning of pixels 2 by 2. Okay, as for the parameters, there was 150 kVs at both lamps and 22.5 watts, because as I said, this smaller tube is able to get to 25, but it is not that stable, so better we stayed here. The experiment duration was 24 seconds for technical reasons, because I exposed the images and only kept them in the memory, in RAM, and then save it as a whole. And of course, you got a lot of data, because in the first case there was 600 pairs of images was in this full resolution, and in half resolution it was even 1,600 pairs of images. So we get always the pair from this direction and this direction. This is the geometrical configuration. For the mechanical reasons, we were limited in the distance of the detectors from the sources, and we were limited to 530 millimeters in both cases. Of course, the magnification in both cases, in both axes, was the same, and it was 2. So it means that the esophagus was exactly in the middle, in between the sources and detectors. Now, this is what you get. If you do the scanning or the imaging with the parameters that I set, and with 15 milliseconds of exposure time. So you see that the exposures, the images are very dark and probably very noisy as well. Of course, because we do not have so many photons. We do not have so much excitation of the detectors. And the only thing we could do is, well, there are two things. One is increasing the time, but it is something that we really do not want to, because on the contrary, we want to get it to the limit of the shortest time possible. to have a good temporal resolution of the process observation. Or you can increase the power to have more photons and bigger intensity of the radiation of the detectors. But this is exactly what we couldn't do because of the weaker X-ray source. So I was thinking how to get a good image out of this. And at the end of the day, what you are looking for is an image, is a binarized image of the particles. You are not really interested in much details about the chambers and so on, but you want to know exactly where the particles are. And it happens that I am an amateur astronomer, so I was thinking, or well, not even thinking, but I said somehow that actually I'm dealing with images with low contrast, high noise, and it's exactly the same what you get in astrophotography. So you have, for example, these images, and you can get image like this if you use good software for extracting the information out of them. And well, after trying to process my images in Python or MATLAB, I then tried to pass these images to the astronomical software, which is called PixInsight. And I tried to make some process to get the binarized image of the bolus. Here, these are the same images. They are already stacked to always one image or one screen from the two detectors. And these are already after some stretching of the histogram. So it is not that dark anymore. And you can see now in real time what we actually got from the experiment. So there are the particles moving. There is a lot of noise, but the scanning speed, let's say, is quite good because we can see the particles even when they are in the movement, although their intensity is different because the movement means that, of course, the contrast is even weaker than if it is stable. And you can also notice that the movement of the bolus is not linear. So in the future, maybe we will reprogram a little bit the process of control of the esophagus to make it more linear. Well, this is how the images were processed then. So this was the original image, and this all was done in astronomical software. This is histogram stretching, the first one. Then we used some noise reduction tools, which are very good optimized in these programs, in these software tools. Some morphological operations, and then binarization, and then at the end of the day, at the end of the process, just inversion to have 0 where is black and 1 where are the particles. Now, when we got, well, these images, and we got, as I said, 600 pairs of these images, each from one detector, from one experiment, and 1,600 from the other one. What can we do with them? How do we reconstruct the 3D scene? So this is the reconstruction principle that we used. These are the detectors, and if there is a tracking particle in the view, in the field of view, it will make some print on the detector, of course. And let's call the line which connects the spot from the particle on the detector with the source of radiation, the projection line. So then if there is some particle like here, and it makes the spot here on this detector 1, and this spot here on detector 2, then of course it has to lie exactly in the place where these two when these two projection lines intersect. Here is another particle, and it's the same story. So it makes the spot here, it makes the spot here, and if I can construct the projection line, I can get the position of the tracking particle. But I also, in this image, wanted to visualize what can happen, because we really, from two views, we do not have so much information. And it can happen that by pure coincidence, this projection line intersects again with this projection lines, which pertains to different particle, because this particle generates this projection line, and this particle generates this projection line. And if for coincidence they intersect as well, then we have here a false detection. And just making these experiments, I then realized that there exists just a whole field of or investigation field, let's say, which is called discrete or binary tomography. And there are some methods how to do it to limit the false detection problems. So in the future, I will have to get more into this and try to learn some other maybe improved methods of reconstruction from only two orthogonal images. What we want to do when we are reconstructing the volume where the bolus is moving is reconstruct this space, which we will call the reconstructible space, and it is given by the projection lines from the corners of the detectors, because this is exactly the intersection of what can be seen in both imaging axes. And the shape of this reconstructible space is not rectangular, it's rather complex. So we will have to resample it to a rectangular block after that. So this is a space, this is the area, let's say, or the place which is interesting for us. Now, if we have this image on one detector, and now just for sake of the visualization in this talk, now here the white means 0 and the black or gray means 1. If we have something like this on one detector, we can make the spatial extension of the detector, like pulling the image from the detector in this direction towards the source, and we get something like this. These are parts of the projection lines actually generated by these particles or these spots on the detector. And we do the same on the second detector. And now, if you remember, I said that the particle has to lie on the intersection of the projection lines. So it means that if I multiply these two matrices, I get intersections, and these are the positions of the tracking particles plus the false detections, I have to say. So this is the principle that I used, or that we used, for generation of the 3D models from each pair of the image on the detector. And there was a very big amount of individual reconstructions. It was again 600 in full resolution and 1600 for binning. Okay, and I am almost going to the end of the talk, because now we will see how then, if I stack all the 3D volumes, how does it look like? And how does look like the transport of the bolus reconstructed in 3D, even considering the limitations that I said, like, for example, the false detection. So now we could saw that here was some movement of the particle here again. And maybe you notice that there are always some particles like aligned or something, and this means that some of them are false detections. This, well, unfortunately, let's say. But still we see that it was even possible to reconstruct it just from the two views. And it means that the principle is, let's say, plausible, but we will have to improve many things yet to have good volumes for making the velocimetry fields. Okay, so just to conclude, the movement of the marking particles was successfully reconstructed with a temporal resolution of 40 milliseconds and even 15 milliseconds. We have some false detection problems doing that, but one of a very simple measures would be to use strictly spherical marking particles, because then if you see here a particle which is not spherical, then it means that it's false detection. So it would be very good, but what we use as marking particles was just a powder of barium sulfate. That's why we have irregular particles and also particles of different size and volume. So in the future, we are thinking about using spherical particles of tin, for example, that you can get from the soldering paste, for example, or you can buy dedicated particles which have some guaranteed shape, and then it could be possible to filter out the false detections. Another problem was that the power is limited by the weaker X-ray source, and this generates the noise because we do not have enough radiation, we do not have enough intensity. But this is the limitation which can be improved buying a new tube, and this is something that we plan. So if it is already applied for, so hopefully we will get a stronger X-ray tube for the other axis as well, and then the scanning of this type could be better because of better contrast. The esophagus control can be also improved, because if we have linear motion, then we will not have these problems of disappearing particles. I will go again here, that you can see that during the fast movement, there are some particles disappearing and appearing again. And nevertheless, what we did now in this project was submitted to the scientific journal, the MVPI materials. Okay, so thank you very much for your attention, and of course I am prepared here for your questions.
Okay, thank you, Dr. Vopálenský, for this interesting talk. And now floor is open for questions, either in Spanish or in English, if you want.
Doesn't matter, actually.
¿Preguntas? ¿Alguien de aquí tenemos preguntas? Verena.
Sí, muchas gracias. Thank you very much for this interesting talk, Michal. I'm wondering whether it could be useful or realizable to maybe embed this dual vision CT reconstruction into a full view CT vision, maybe of the esophagus without movement, to get the environment in this 3D reconstruction that may be helpful to identify whether the movement was tracked correctly or whether it might be not. Well, so I'm wondering whether it might be useful to reconstruct the esophagus without movement first, identify the voxels that with particles that start to move might be changing when now moving esophagus in action can only be viewed from very few spots, and maybe these few spots may change a little to avoid the mismatch of the particles. Some ideas.
You mean to make a regular tomography in the beginning?
Yes.
Okay. With the bolus inside already, or with in a stopped state, let's say, of the esophagus, make a fast tomography, but moving the esophagus by one rotation, which is possible, and then have a good starting point for the identification of the particles inside. Well, yeah. I think it's a very good idea, because as you saw, we can extract some information, but of course all the details are missing, of course. So making you are right, but it is not possible to make it from the two views, of course, because these two views are the reason that we have to sacrifice, let's say, a lot of information that we can get from the regular tomography, and just be interested in the contrast spots, so in the contrast particles. Yeah, but you are right. Yeah, it would be a nice starting point. Yeah, the problem is a little bit technical, that when you put there the bolus, it means the baby food, and you start the process, you would have to stop it after some time when the bolus is already somehow distributed inside the esophagus. Then make one one rotation, make some tomography, and then begin to make this extreme, I would say, extreme tomography that we did with 15 milliseconds, but you would have already a good starting point. You would know exactly where the particles are, and maybe it could help to exclude the obvious false detections. Yes.
Okay. Do I have the opportunity for a second question?
Yeah, of course.
Okay, so I see that the X-ray guns have different energy potential. You are operating at the same level in this observation you showed us. I'm curious whether using different energies might improve the overall vision of the reconstruction, operating like dual energy tomography, which is I understand useful for medical applications. Are there some applications using dual energy with the Toraton?
Well, yes. The answer is yes. This is when the Toraton was constructed, it was equipped with two X-ray tubes, and one was meant for the tomographies of like metals, or I don't know, concrete and these things. And the second one, the small one, the tube which has limited power, has the transmission target, and its advantage is that it has very small spot. So, and it has the nanofocus functionality. So we can go with this tube down to 1 micrometer of resolution, but at the cost of long scanning time, because you need, you do not have really big power. And the reason for this was that we would have on one table two different tubes for two different, or for various different tasks. But then it is a little bit limiting because of the power. And as for the dual energy, we use this thing for dual energy measurement, because normally you can do dual energy without any problems. If you have a static object, you can do it without any problems, like successively. So you make one rotation and then you make second one with different parameters on the tube, and that's it. But sometimes there are cases that you need to make it simultaneously. You need to have you just cannot make it subsequently. It is the case of, for example, the experiments where you observe how water or some other agent is penetrating into some material. And for such an application, it is really a good choice to use the dual energy, because then you can subtract the matrix, let's say, and see very well the water or some, I don't know, iodine or whatsoever, which is penetrating to the object. But you need to see it at the same time, of course. So for these applications, it is really a very good possibility or functionality of Turatom. But for the case of the esophagus, I wouldn't say, well, what we tried to do was to get the energy to the maximum possible. And as the second, the smaller lamp has the maximum acceleration voltage of 160, we made it on 150 to have some, you know, some safety zone. So actually we were doing on the limits of the lamps, yeah.
So if particles are multi-material, then it might be interesting using dual energy, but as long as the particles are the same, use the same energy?
Maybe, but the problem is that you, what do you need is the image of the particles, and you just have two directions. So actually you use the lamps. I mean, to make it in dual energy wouldn't give you probably the information that you are looking for, because you need the information of the position of the particle at the first, and the dual energy can be used if you make the normal tomography and you do it on two energies. I don't know if it could be somehow combined. Maybe yes. Maybe it could be somehow combined, but I think that for this case, as you said exactly, that the particles are of the same material, like it doesn't bear any advantage for you to make it on dual energy, I would say, because you do not need to distinguish anything else than just the position of the particle.
I understand. Thank you so much.
Okay, thank you.
Thank you, Verena, for your question. Any other question? Nasser.
Hola, Michal, un gusto.
Hola.
Voy a preguntar en español.
Sí, pues, espero que voy a responder.
¿Cómo salen las imágenes en este sistema si son muestras como madera o árboles? ¿Hay contraste con este tipo de material?
Sí, es que nosotros hicimos muchas cosas con madera, porque, por ejemplo, la gente de las facultades biológicas, ¿no? de Brno y Praga estaban curiosos de la humedad de la madera, y entonces se hicieron estos ensayos. Y lo que es bueno con rayos X y tomografía de madera es que aun cuando visualmente no se ven los, ¿cómo se llaman ahorita? Los círculos de años, ¿no? En el árbol. No sé cómo se llaman exactamente.
Los anillos, creo que le dicen.
Los anillos puede ser. Y aunque no se vean ópticamente o visualmente, se ven en el tomógrafo porque tienen otra densidad, y entonces, aunque no tengan una diferencia de color visual, ahí se ven muy bien. Y eso es el caso, por ejemplo, del árbol de tile, ¿no? Que o tila, no sé exactamente, tile, ajá, en latín sería tilia, ¿no? Y ahí esa madera se utiliza para hacer estatuas bueno, parroquias, digamos, ¿no? Y así. Y nosotros a menudo hacemos una investigación de estas estatuas de madera y ahí los restauradores ven de qué tal número de piezas estaba hecho y cómo está todo compuso y tal. Y también ya hicimos un ensayo dendrocronológico, ¿no? Que basado de los años o los añilos de madera, se podía identificar cuándo cayó este árbol, de cuál se hizo una obra artística. Entonces sí, la madera se ve muy bien normalmente. No se ve bien una madera que ya esté conservada, porque tuvimos también un ensayo con el museo ahí en el alrededor, que dijeron que han encontrado como que algunos vasos de madera en una cisterna, ¿no? En una cisterna que ahí estaban construyendo una casa o algo y pues descubrieron una cisterna medieval y ahí en el barro o lodo se conservaron muy bien las cosas de madera, porque ahí no se descomponen porque no hay oxígeno, ¿no? Pero luego ellos cuando lo sacan de allá, lo tienen que conservar y se hace de una forma que se cuece con algún polímero. Y este polímero luego allá en la madera, de alguna manera, reemplaza, yo no sé si agua o celulosis o algo, pero este tratamiento luego llega al factor que se homogeniza mucho la densidad de la pieza. Y entonces en estos objetos no hemos visto las estructuras de madera, porque ya estaba homogenizado por este polímero o algo de conservación.
Gracias. Entonces surge la pregunta, si quisiéramos hacer un sistema así portátil, ¿existen componentes como de bajo costo que uno podría usar para hacer un tomógrafo portátil de rayos X?
Bueno, pero yo creo que este tomógrafo que aquí tienen, ¿no? Que está disponible aquí abajo con doctora Verena, ¿no? Y doctor Leopoldo Ruiz, pues sirve para estas cosas muy bien, porque tiene buenos parámetros como tiene nuestro Toratón, tiene el mismo detector. Entonces yo puedo decir, sin hacer un ensayo, puedo decir que estas cosas de madera se pueden hacer muy bien hasta aquí, en el tomógrafo que ya tienen. Pero yo no sé exactamente cuál tipo de experimentos le interesaría, ¿no?
No, exactamente lo que estabas diciendo. Si queremos ver dentro de un árbol, pero el árbol está vivo y está lejos, obviamente uno tendría que hacer un sistema sencillo de fuente de rayos X y detector. Mi pregunta es si ya están surgiendo en el mercado componentes más baratos en el rango de rayos X, como está pasando en otros rangos de frecuencia.
Ajá, bueno, sí, pero es que normalmente estas cosas son bien caras, ¿no? Porque el detector Dexela que nosotros utilizamos por allá, por ejemplo, cuesta como $1.000.000 o algo así. El detector que utilizan aquí los compañeros mexicanos aquí, que nosotros también, es el XRD 1611, y él me costó en la República Checa $4.000.000, ¿no? Y pues, y luego fuente de radiación, un tubo de rayos X, bueno, cuesta como por allá, o lo que nosotros utilizamos también tal vez se puede conseguir un poco más barato, pero pues no creo. Y cuesta como 3 millones, ¿no? de pesos mexicanos, digamos. Entonces, pues sí, sí cuesta algo.
Muchas gracias y gracias por la plática.
Thank you, Nasser, for your questions. Any other questions? Anyone? Spanish or English? I have a question. Thinking in the application of this technology, is it possible that the body fat can somehow scatter the X-ray in the measurements of the particle movement?
The body fat?
Sí, la grasa corporal puede tener, puede ser algún impedimento para, o es como transparente.
Yo creo que no, porque pues sí tenemos pues depende de los marcadores, ¿no? Pero nosotros utilizamos este sulfato de bario que es muy contrastante, ¿no? Y entonces con eso la grasa no sería un problema, ¿no? Porque la grasa, ¿qué es? ¿No? La grasa son carbohidratos, ¿no? Entonces, sí, yo creo que ahí con eso no debería ser problema, ¿no?
Ok, muchas gracias.
Pero el problema que sucede luego,
sí.
si quisiéramos aplicar algo así en medicina, digamos, es que nosotros normalmente cuando hicimos o hacemos estos experimentos, no nos interesa la dosis, porque pues no estamos trabajando con el cuerpo vivo. Pero luego nosotros utilizamos pues ya una energía bastante grande, ¿no? De 150 kV, pues es bastante grande para los, ¿cómo se llama? Los tejidos orgánicos, ¿no? Y entonces eso yo no estaba investigando todavía cómo luego se puede aplicar esto, pero como hacerlo para el uso a los pacientes, pero eso sería la primera pregunta y el primer problema. Porque significa, bueno, si quiero ver en tiempo real y en 3D cómo se está moviendo el bolus en un humano, y si eso dura como 4 segundos, eso significa que esta persona va a recibir por 4 segundos alguna dosis, ¿no? Y pues eso sería la primera pregunta, cuánto es o cuánto no es y tal. Porque hasta que en medicina todo o el criterio que se utiliza es siempre la dosis, ¿no? Y nosotros, el criterio para nosotros es la calidad de imagen, ¿no? Pero hasta que, lo digo así que pues no se pueden dar el lujo en medicina de hacer imágenes de cualquier calidad, digamos, porque eso significaría tal vez más potencia o más tiempo o algo así, o más ángulos. Bueno.
Claro, cuestiones de seguridad para el paciente.
Sí, claro. Sí.
Por supuesto. Muy bien, muchas gracias, doctor. ¿Alguna otra pregunta? ¿Alguien más? Por aquí. Ok, bueno, yo tengo otra curiosidad. Se habla de este desarrollo para ver el paso del bolo a través del esófago. ¿Qué otras posibilidades se pueden tener en medicina? Bueno, más bien, ¿qué tanta posibilidad hay de que se pueda aplicar esto, por ejemplo, para el torrente sanguíneo, por ejemplo, para ver obstrucciones en el torrente sanguíneo?
¿En dónde, perdón?
En la sangre.
Ajá. Bueno, eso no lo sé, la verdad. No puedo decir porque pues no tengo experiencia con esto. No sé qué. Yo creo que sí existen también marcadores que se pueden poner en sangre, ¿no? Como yodo y así, ¿no? Que se utiliza.
Sí.
Ajá, eso,
Sí,
pero
medios de contraste
pues, sí,
yodados.
perdón, pero eso no puedo decir, no tengo ninguna experiencia, entonces no quiero decir algo que no sé con seguridad.
Claro, apresurado.
Sí.
Ok, muy bien. ¿Alguna pregunta por aquí? del público, tal vez del MADIT. Ok, bueno, por lo pronto no tenemos más preguntas. En todo caso, pues estarán dando más preguntas una vez que subamos el video a la plataforma de YouTube del ICAT. Y pues no queda más que agradecer al doctor por su interesante presentación. Muchas gracias.
Muchas gracias por invitarme.
En breve le estaremos haciendo llegar su constancia de participación. Y también muchas gracias a todos los asistentes. Que tengan un buen martes. Hasta luego.
Gracias, hasta luego.
Bye, bye, Dios.